Okay, well, I thought I'd make histones, chromatins, and RNA kind of easy for everyone. Seeming that I find a lot of stuff online, I thought maybe I can give back. So we'll start with my professor's slides. And as we see here, my professor has nicely put down the multiple levels of DNA packaging. Okay. So basically, what is this slide telling us? It's telling us that, first of all, DNA, let me just state, is over 2 meters long in length, okay? And there is no way we can fit 2 meters in a tiny little cell, right? Now, she's indicated over here, and let's see how this works. Let's go for blue. She's indicated over here 2 nanometers, okay? That's just a short region of it, okay? But just remember, the whole DNA is relatively almost 2 meters long. Now, what happens is, I mean, we all know that DNA is a double helix and it has sticky ends, meaning, you know, if you kind of bend it and stick it together, you know, it'll bind with the others. You want to keep it as to itself as possible because there are a lot of interactions, correct? So what happens? This octameric thing, let's just put it this way for now as we're starting out, comes in, and it's kind of like a reel. And this is called a histone. It comes in and DNA actually wraps itself around it as we see here. So it's kind of like the hose reel. Let's picture it that way. Now it's about 195 base pairs long, what we have, wrapped around here. And then as you see here, there's this little leftover piece kind of to connect, you know, because it's filled up on that end, so it goes to the next one. And this is what they call a linker. Sorry, I'm using my mouse, so. Okay, so this is what is called a linker. Fancy name to say that it's linking one reel to another. The linker is about 27 base pairs long, okay? So this is the first level of packaging, as she had nicely stated over here. So the first level of packaging is seeing this beads on a string kind of thing, where chromatin begins to form, because this is not chromatin, this is the beginning of it. And she stated that the initial, I would say, phase of it is this beads on the string, you know, form that's about 11 nanometers long. Now, what comes in here is something called histone 1, and it kind of stabilizes this mechanism. And once this mechanism is stabilized, it kind of like smushes them together. They all like come together. And what they do, the way they come together is like they come together just closer to each other, okay? So they just come closer to each other and they just kind of connect. And this package, this level of it is called, you know, the 30 nanometer pack, which is the level that it's ready to go. Basically, what happens is that as it comes together, it kind of loops like a little flower, okay? Let's just picture it that way. And this little flower is what makes up our chromatin, because you've got a lot of these little flowers going on around here, okay? And this is how it's packed. Now, it does not necessarily mean that it's super tight, okay? Because it doesn't, a chromosome has to be accessed. So if it's like super, super tight, that's no good to us because then we can't read it. So it's still going to be like a flower, but proteins are going to be able to access it here, here, here to read it and to be able to decode it. Though the most condensed section of the chromosome, as we see here, is the supercoiling. That's the last step that happens. It's an additional coiling step that happens after all these, you know, after this coiling and the little flower and the histone 1 coming in and topoisomerases, the next step is this supercoiling. So we're going to say it's supercoiling, okay? And this supercoiling actually causes it to be super condensed. Why is this necessary? Well, this is necessary when we're going through mitosis. Because if the chromatin is not If it is not super condensed, then there's access, and all this stuff that's going around is going to ruin it. So it needs to be super, super tight. That's the only time we will find chromatin super, super tight. You know, because that's the time that it needs to be tight so that way it can split during mitosis, okay? Now, here's an electron micrograph, as she shows, of these nucleosomes like beads on a string, okay? You see these little beads. This is the open one that we had, the 11 nanometer one. And this is the 30 nanometer one going round like a little circle, right? Flowers, okay? So packaging into a chromosome required for cell division. We just said that. So over here, we've got tons of little beads, hence the 2 meters fitting into this chromosome, yes. So here's the centromere. This is where everything needs to detach, okay? That's the center of it. So as we see here, except for the M phase, the DNA is packed into chromatin rather than chromosomes, okay? So what is the whole reason of this supercoiling here? The whole reason for this supercoiling is to become a chromosome, okay? So this is when we split. We need the chromosome to split what? The sister chromatids, okay? Wow, I'm getting the hang of this mouse thing. Okay, so these need to split, right? So that's the whole point of this phase, having the necessary of having this extra supercoil, okay? And this is where the histone comes in. Over here, and over here, it's more relaxed, okay? It's more relaxed. It's packaged into chromatin because what? We need to access it. We need to know what we're reading, how we're reading it, and what we're going to do with it before we split, right? Okay, so the packaging into chromatin fits the DNA into the nucleus, like we said. 2 meters, got to fit into the nucleus. Protects the DNA, like we said. It keeps it apart. We have this hose reel going around to keep it so it doesn't interact with each other and stick. Because if you take a big long hose and you try to cram it into a little hole, it's just going to smush and bend and, you know, not work properly, you know, if you keep it packed for too long. This way, if it's on the hose reel, it'll be a little bit rusty, but, you know, it'll open up just like DNA. It organizes segments of the DNA to allow transactions such as gene expression, like we said. It stretches out to allow some reading so that way you know what you need to do. And this also distinguishes between eurochromatin and heterochromatin. And we'll get into that right after in my further videos. Now before I close this off, I thought I'd show you a recording that I have, which is amazing. And I found this from a German site, but it's in English, which sums it up for us. Sorry, I can't expand it any bigger. It won't go bigger.
The total length of the DNA in a human cell is approximately 2 meters. The DNA double strand that is wound into an alpha helix only fits into the cellular nucleus because it is folded in a complex manner. Structural proteins are required for this folding. Together with the DNA, they are termed chromatin. Octamers comprised of histones bind to DNA, which wraps itself around this protein core in the process, thus forming a nucleosome. Between adjacent nucleosomes, a piece of DNA, the linker DNA, remains free. A characteristic string of pearl structure is formed. The nucleosome chain is folded to form a 30 nanometer fiber. An additional structural protein, histone 1, stabilizes this fiber. Certain regions of the 30 nanometer fiber, the scaffold-associated regions, couple to structural proteins, among them the topoisomerase. In this process, the 30 nanometer fiber forms loops. The filamentous DNA protein complex forms the so-called super twist, which is further twisted in an additional coiling step. With this final step, the complete condensation of chromatin has been achieved. This is the organizational state of the chromosome during nuclear division, mitosis.